Major funding for this project has been provided by the Peter Moores Barbados Trust and additional funding from the University of the West Indies.
To see a world in a grain of sand and a heaven in a wild flower. Hold infinity in the palm of your hand and eternity in an hour. William Blake could have been writing about the myriad of things in the universe that at its heart and soul are described by mathematics.
It was well over 2,000 years ago that the Greek mathematician Pythagoras showed that in any right angle triangle, the square of this side plus the square of this side gives you the square of the hypotenuse. Indeed, we could not get through school without having been taught that. Pythagoras is known as the father of numbers. He led a school of thought that believed that all things around us could be explained and understood by mathematics, or as he so elegantly put it, all is number. Join me on a journey as we discover that mathematics is the heart and soul of all things around us, even when we least suspect it.
All science depends very heavily on mathematics, which is the language of science. Now, you may think that as a biologist, you do not need that much mathematics, but when you think of the sophisticated statistics which are used by biologists as they examine the natural world, then you will see that you perhaps have a quality of mathematics which is beyond many other people. Even in social sciences, where they tend to think of themselves as somehow different, they depend very heavily on graphs and analysis of graphs, which is of course mathematics. Everywhere we go, there is mathematics.
Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. These are the words of Mandelbrot, the man who discovered the geometry to describe such complex patterns known as fractals.
And first I should try to explain in a very superficial fashion exactly what a fractal is. Everyone knows that a line is one-dimensional and that a plane is two-dimensional, a cube or a sphere three-dimensional, and so on. But what many people do not realize is that there are objects which have a dimensionality between 1 and 2 and between 2 and 3. They have what is called a fractal dimension, which may be 1.6, 1.4, 2.3, or anything like that. A prime and simple example of that is a coastline.
The fundamental question is, how long is a coastline? Well, the answer depends on the measurement stick used. If we look at the coastline of Barbados, a meter stick will give you a shorter length than if you use a string which can allow you to go around every stone and pebble. The more you increase the accuracy of your measurement, the longer your distance becomes. This is a property of fractals. Fractals are figures with an infinite amount of detail. The more detail you measure, the size increases. There is structure at all scales.
Trees, leaves, all of these things have fractal characteristics. The characteristic of what is called self-similarity.
Self-similarity is easy to see in a tree, where at every scale you look, the pattern repeats itself, from the spreading veins in the leaf to the branching of the whole tree. Dr. Donna Kamisyang is a mathematician at the University of the West Indies who brings a little order to the world using chaos theory.
Chaos theory is what I'd like to talk about. It's a relatively young science, and it's the study of things that are not predictable. Things that might seem to be random, but there is some sort of pattern in it. Things that if you change the initial conditions slightly, the outcome could be greatly different than what you would expect. This is why it's a relatively young science. Chaos is something that's not understood but is necessary to be understood for certain things that might even occur in the human body, the heartbeat. People with chaotic heartbeats often find themselves in hospital, and the doctors have to try to understand what to do to make the heartbeat more regular. So chaotic patterns in the brain is also important in order to understand what is happening inside of the brain. If you think that there are these alpha patterns that can be captured by a person who's resting, can you imagine what would happen with a person who's alive and well? And so there are many things that need to be understood and are not yet understood by these conventional laws of mathematics. And chaos theory, for that reason, is a very interesting, young, and unexplored science.
An interesting application of chaos theory is the butterfly effect.
The butterfly effect is quite a famous example. If a butterfly flaps its wings, the air pressure around the wings could change, just minimally. But that minimal change, as we said before, chaos theory deals with the way that a pattern could change tremendously based on a small change in initial conditions. Well, if a butterfly flaps its wings, you can imagine that the pressure change might later generate a hurricane in some other part of the planet.
Mathematics is used even in climatology. Adrian Trotman is a researcher at the Caribbean Institute of Meteorology and Hydrology whose work relies heavily on statistics.
One of our tasks in this section is to be able to develop a number of climatological products which can be used across multiple sectors, water resources, agriculture, biodiversity, ecosystems, you name it. And these products that are developed because of the nature of climatology, which is the statistics of weather, essentially we're fitting distributions, for example, normal distribution, gamma distributions, to try to better understand and to better show to others and those in those sectors how the weather is operating, how is it developing, whether it be trends, frequencies of occurrences, return periods. All this is important information for people in these sectors so that they can plan, so they can develop strategy and so on.
Well, as an applied mathematician, I can attest to the fact that mathematics is used in many different fields, many different avenues, in many disciplines. And it's necessary because in order to understand any process that repeats itself, or not just repeats itself, that has a pattern or evolves in a certain way, you must understand first or be able to build a model that would help you to understand or predict what will happen in the future. So anything that has predictability or needs to be accounted for or needs to be added up or estimated in any way would require mathematics. So it's a very versatile field, and there are many avenues for research and future development.
I'd like to get that one. Thank you. Making sure you get the right change is certainly mathematics, but it goes much deeper than that. Mathematics is a powerful tool in understanding the world of business.
To manage the outcome of profitability in your favor, it means you have to manage everything else, and that depends on mathematics, it depends on numbers, it depends on targets, it depends on having numbers to let you know as markers how well you're progressing or how badly you're doing. If you're dealing with sales, numbers are important. If you're dealing with marketing, targets and numbers are important. If you're dealing with productivity, numbers are important to measure productivity. So in business, numbers are fundamental, they are basic, and everything depends in business on your appreciation of the value and significance of numbers. Because as they say in business, you can only manage what you can measure.
It has always been easier for humans to represent that which they can see over what they cannot. Like right here, I have one stone, and if I get another one, I have two stones. Two stones, take away one stone, leaves one, and one, take away one, leaves none. But how is that any different from having no fruits or no leaves? That concept was so difficult that it took humans centuries to be able to grapple with it and to be able to represent it. Or as the Greeks said, how could nothing be something? Today we know that can be represented by the zero.
The simplest number scale, therefore, can consist only of zeros and ones, the binary scale. This is the language of our high-tech world of information, technology, and communication. All the manipulation that is needed is for a 1 to represent an on state and a 0 to represent an off state. Using these two bits of logic, the most complex engineering design can be built using digital electronics. Numbers, they are everywhere. Starting with a 0 and 1, each new number in the series is simply the sum of the two before it. We have just built the set of magic numbers known as the Fibonacci series. We never have to look far to see these numbers in nature. The magic number 5 is a favorite with flowers and plants. If you divide each Fibonacci number by the previous one in the series, they all converge to the ratio 1.6. This number is known as the golden ratio and is used in architecture and art due to its pleasing sense of balance. The Parthenon in Athens and structures such as the Pentagon and Washington Monument all utilize this golden ratio, even some well-known faces. If a rectangle with the ratio of the sides equal to 1.6 has the section which is a square removed, the remaining figure has the same golden ratio. This can be repeated numerous times, and when the opposite ends of the square are connected, one of nature's favorite forms emerges, the spiral. The sunflower is a striking example of this. The seeds appear to be spiraling outwards. Nature has found an optimum packing method using numbers. Pine cones, ginger lilies, and pineapples all exhibit this pattern. The harmony of music is based in mathematics. When the notes are in certain ratios, music becomes a delightful sensation. Rhythm and pitch are born. Noise is a mixture of many different frequencies at the same time with no clear pattern. It was Pythagoras who noted that the sound of a hammer on a metal produced pleasant and discordant sounds. He discovered that when their masses were simple ratios like 2:1 or 4:1, then the notes were in harmony. The ancients produced wind and string instruments with the spacing of the holes and lengths of the string in exact mathematical proportions. The tone that is produced by a vibrating string depends on its length. Tuning a guitar is nothing more than adjusting the tension in the string with mathematical precision.
The beauty of mathematics is that it does not matter if you are at a river's edge on a Caribbean island or in the far reaches of outer space. It does not depend on a place or time, a people or culture. It is universal in its relevance. It describes that which we can and cannot see, choreographs the dance of the atoms on the tiniest scales while describing the universe on the grandest scales. Nature speaks, and if we listen carefully enough, it speaks. Mathematics